Hello, my name is Elliot Kane, and in this presentation, I will provide a brief survey of piston engines in aviation. First, I'll talk about how they work, then I'll go through their history and evolution during the 20th century, and then I'll conclude about their current status today. I should mention that there are a few different names for piston engines, most common being internal combustion engines and reciprocating engines. And these both give some insight into how they work, which we'll see just now. So the main operation of a piston engine is the combustion of fuel and air inside the cylinder of the engine. On the diagram on the right, you can see a schematic of a cylinder in the 4 different stages of the Otto cycle. The Otto cycle is simply the name for the 4 strokes, and it's the thermodynamic cycle which the air and fuel mixture goes through to produce the power that the engine is there for. And so I'll just briefly run through the 4-stroke Otto cycle. Intake stroke pulls air into the cylinder, and the piston moves down. The compression stroke, the piston moves up and compresses the air by reducing its volume. In the power stroke, a spark plug ignites the fuel-air mixture, which pushes the piston down again. And then in the exhaust stroke, the piston moves up, expelling the combustion products out of the cylinder through the exhaust valve and out of the engine through the exhaust manifold. And I'd like to show you a brief clip of how the piston moves within the cylinder. You can see here it translates up and down, and you can also see the exhaust and inlet valves moving at the top of the screen. So the role of this combustion is to move the piston up and down, which through the connecting rod turns the crankshaft. And once the crankshaft is rotating, that is where the power of the engine comes from. You can use the rotating crankshaft to power a number of different things. For an aircraft engine, that would be the propeller. The propeller is essentially the mechanism by which a piston engine produces the thrust that an aircraft needs to fly. And it works by the same aerodynamic principles as a wing. It creates, due to the shape of the blade, it creates a pressure distribution, which the net force of which acts forward, which is thrust. And you can just think about it as sort of a sideways wing, as a very simplification. An interesting aspect of propellers is that they move a large amount of air relatively slowly. This results in a very high propulsive efficiency, but it also means it's not the optimal method for producing large amounts of thrust. We'll get more into this later. And also for the first period of propellers, starting with the Wright brothers, and then all the way until 1930s, propellers were fixed pitched, and that meant they were only optimal at a specific design condition. When planes were slow, it didn't really matter that much, but as planes became faster and faster, the difference between the takeoff and the cruise conditions were so great that propellers could not be good at both conditions, and specifically the propeller's efficiency was only good at one of them. The invention of the constant speed propeller changed this and allowed propellers to be efficient, to operate at their peak efficiency across the range of flight conditions. So now I'm going to talk more about the evolution and history of these engines. Starting with the Manley engine from 1901, which powered Samuel Langley's unsuccessful attempt at a flying vehicle called the Aerodrome. And that attempt failed, but it was not due to the engine, which was a spectacular piece of engineering. You can see a picture of it here. It was a radial configuration with 5 cylinders. Radial means that the cylinders are arranged in a circle around the crankshaft. It it had an astonishing amount of power for its weight at the time, and it's simply a marvel of engineering, which is why I've included it here, even though it technically was not on a flying vehicle. Starting with the Wright brothers, they had a much simpler engine. It's a 4-cylinder inline. You can see the cylinders are horizontal and next to each other, which is what inline means. And it produced much less horsepower, only 16, and that for only a brief period before dropping down to 12. And it was also slightly heavier, but this engine attached to the Wright brothers' efficient propeller was more than enough to lift the Wright Flyer into flight. Now I'd like to talk about a period of engines that are very interesting to me in particular. These are rotary engines. And first, I should mention that these are not to be confused with the Wankel rotary engines that powered Mazda automobiles. These are much different. They, on first glance, appear to be a radial engine due to the configuration of the cylinders. However, they have a very interesting operational method where the cylinders and the crankcase, so just the main body of the engine, actually rotates, while the crankshaft, which is what usually rotates in an engine, is fixed to the airframe. Now, this may seem odd, but it actually had several advantages. Probably the most important was that it offered excellent cooling, which was an issue for early engines. It also meant these engines were compact, which was helpful for maneuverable aircraft as well, such as fighters in the First World War. It was free from vibration, which meant there's no need for a flywheel. And all of these advantages resulted in a low weight, which was extremely important for early aircraft. I'd like to show you a brief animation of one of these engines. You can just see how the engine rotates. The cylinders rotate, but the crankshaft is fixed on the right side of the screen. One of the most famous rotary engines was the Clerget 9B, and it powered the famous Sopwith Camel. You can see the specs here and the plane on the left. And however, the era of the rotary engines ended in 1918 at the end of the First World War, because inline engines and standard radial engines had become they had evolved and had more advantages. There's also a number of peculiar disadvantages to the rotary engines. First, they operated on a total loss oil system, which meant that their supply of lubrication for the engine was limited. It was simply pumped along with the fuel into the pistons or into the cylinders, and then ejected during the exhaust stroke. And most of that excess oil was splattered onto the pilot. So that's an interesting side effect. Another one is the gyroscopic effects of these rotary engines significantly affected the handling of these aircraft. It made, as you can imagine, a large mass of metal spinning at over 1,000 RPM produced quite a significant torque on the airplane, which made turning in one direction extremely easy and turning in the opposite direction quite difficult. And it also made for interesting takeoff and landings. And then there are a few other disadvantages, such as the RPM limit and the cost of manufacturing, which spelled the demise for the rotary. It was replaced by engines such as the Hispano-Suiza, which was the best inline engine of the First World War. It's a V8 engine. You can see the name comes from the configuration of the cylinders, which are in two banks on the engine at a 90-degree angle. and it was made of cast aluminum, which you can see in the crankcase here. And you can see the specs and how it increased in power over time. But this was to be the first inline engine that was really successful in airplanes. More about the HISO, as it was known. It had one weakness. It was susceptible to exhaust valve burning because it didn't have very efficient cooling for the valves. And it was famously used in the French fighter, the SPAD-13 from World War I. The eventual successor of the Hispano-Suiza was the Rolls-Royce Merlin. It was a V12 engine, which powered a number of famous aircraft in the 30s and 40s. An important engineering improvement is that it's supercharged. Superchargers, basically, they take some of the power that the crankshaft has, the rotating crankshaft has, uses that to power a centrifugal compressor, which increases the pressure and density of the air entering the cylinders. So it just makes the combustion more volatile, more powerful, which increases the power. The reason why superchargers were so important on aviation engines is that they effectively reduced the altitude of the aircraft in terms of the power produced, because as you go higher in the atmosphere, the pressure drops, which reduces the effects of the combustion. And you can see several examples of the different variations of the Merlin here. As I mentioned before, the Merlin and other inline engines of the time were essentially just the result of advances in engineering, manufacturing. The basic concept was the same, but just improved upon by the supercharger. High octane fuels increase the power of the combustion, and chemical additives for the coolant increase their effectiveness at high altitudes and decrease the weight and size of the radiator. Another type of aviation piston engines are the standard radial configuration, which the Pratt & Whitney Wasp was the very first one that it featured all the important components of a modern radial engine, 9 cylinders, and I'd like to reiterate that for standard radial engines, the crankcase and the cylinders remain fixed to the airframe, and only the crankshaft spins along with the propeller. The double Wasp was the evolution of the standard radial. You can see it has 2 banks of radial cylinders, so 18 total, and it was supercharged. It powered many famous aircraft in the Second World War, both commercial and military. One of the key advancements that was unique to radial engines was the cowling. The NACA cowling from 1929 really revolutionized these engines because it vastly decreased the drag that they created with their large frontal area. And in fact, it also improved the cooling by introducing some baffling into the cowling in the cylinders. And overall, once cowlings were added and liquid cooled, or radials were preferred to liquid cooled inline engines because they were lower weight, they were less complicated and required less maintenance. And they were the preferred approach for commercial aviation. Military aviation was more complicated with different factions, but they were probably the better of the 2 options. And finally, it was not to last forever. With the advent of turbine engines in the 1940s and then their application in the 50s, piston engines were phased out of aviation. you can see in the figure on the right that they're simply only good at small speeds. And so when aircraft want to fly faster, it's not efficient or practical for them to have a piston engine. One reason for this is that propeller engines suffer a transonic speed limit. When they're flying transonic or near transonic, the propeller tips will often exceed the speed of sound, which creates a large amount of drag and greatly reduces the efficiency of the propeller and makes it impossible for them to fly any faster than that. Compared to turbine engines such as turbofans, turboprops, even turbojets, piston engines were very complex, had a lot of moving parts, which made the reliability worse, and this reciprocating nature of the movements made them more susceptible to failures and breakdowns. And finally, their size was inhibitive. They cannot produce the amount of power that turbine engines could for the size created. They would simply be too large, and it would be a matter of diminishing returns. However, that is not to say it is that we should ignore piston engines. They are a fascinating topic, and we can still marvel at the engineering genius of those who created them and simply their role in bringing aviation to the state it is today, because without these engines, the airplanes would not have been able to take flight. And I think it is worth it is worth knowing a little bit about the engineers and their creations in whose footsteps we follow today. So thank you for watching this presentation. I hope you enjoyed it, and I hope you learned at least something. And feel free to reach out to me if you have any questions. I'd love to answer them. Thanks again.